Ladies and gentlemen, welcome back to the Simkins Physics Corner. It's Mr. Simkins here with some free fall, but also toss-up problems. So let's recap some of that free fall stuff that you learned in the last lesson. We have 25 meters here, and it says a flower pot falls from a window 25 meters above the sidewalk. So that's 25 meters. Now, in math class, this would be called the x-axis, so this would be the y-axis, and we say y is how high. In other words, the variable that we use for vertical distance is 25 meters. First question says, how much time does a passerby on the sidewalk below have to move out of the way before the flower pot hits the ground? Let's go ahead and take a look at that one. How much time? Well, if you look at your equation sheet, you'll see the equation t equals the square root of 2y over g. So that's going to be 2 times 25 meters divided by 9.8 meters per second squared. And that's going to be the time it takes to fall there. So square root of 2 times 25 divided by 9.8, that's going to be 2.25 or 26 seconds. That's how long it's going to take to hit the ground. How fast is the flower pot moving? Remember, fast is like speed, or speed with direction is velocity. And if we look at our free fall equations, we see v equals gt. Remember, this only works if you drop something from rest, which we are doing, so it does work. We can use this v equals gt. This is 9.8 meters per second squared times 2.26 seconds. And that is going to get us 9.8 times 2.26. That's going to get us 22.1 meters per second. So that's how fast it would be going when it hits the ground. So this is just a quick recap. We saw these three equations. We saw the time equation, the velocity equation, and then the time equation rearranged for distance is just 1/2 gt squared. A little something like that. What happens, though, that's all for dropping something from rest. What happens, though, if we toss something up in the air? All right, well, think about this. There's a beauty and a symmetry to nature, is that if I toss something up, like this coin toss here, if I toss something up, it's going to take the same amount of time to come back down as it did to go up. This is symmetrical. If you throw something up and it comes back down and you catch it at the same height that you threw it from, it's going to be a symmetrical distribution of time. In other words, if it takes 1 second to go up, it's going to take exactly 1 second to come down, which means it's in the air or has a hang time of 2 seconds. So let's take a look at this idea. A tennis ball is thrown straight up like this. V equals 22.5 meters per second. So it goes up and it's come back down. How high does the ball rise? So we're looking for how high. That would be y equals 1/2 gt squared from our very special free fall equations. Now you may be saying, Mr. Simkins, you're not free falling, you're tossing up in the air. But think of it this way. The reason we can use the free fall equations is because we assume that we drop it from rest at the top. Check this out, though. If I throw something up from the bottom, it goes up, 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 slows down, slows down, slows down. What happens when it gets to the top? Well, it stops, of course. That's why we can use these free fall equations for a toss-up problem. We toss it up, same thing would happen as if it came back down. But we have to keep in mind if it doubles or not. I'll show you what I mean by that in a second. How high does the ball rise? It'd be 1/2 g, 9.8 meters per second squared, times time squared. I don't know the time. I can go get it, though. I can get it by t equals the square root of 2y over g, which is also in our special free fall equations. So I take the square root of 2 times, I can't do that. Another dead end. Why not? Because we don't know y, Mr. Simkins. Well, here's the deal. I do know v. So if I know v, I can use v equals gt, right? Only for free fall, but here that rule applies. G is 9.8 meters per second squared times time is going to be t, and my velocity, which I do know, is 22.5 meters per second. So 22.5 meters per second equals 9.8 meters per second squared times time. To solve for time, you divide both sides by 9.8 meters per second squared, and you get your time over here of 22.5 over 9.8. Oops, sorry. That would be looking like 2.3 seconds. So that's how long it would take to go from the bottom up to the top. T equals 2.3 seconds. Oh, okay. Well, let's go back. Let's not forget question A asks us how high does the ball rise. So this is y equals 1/2 gt squared. Now, a quick note here, you're only squaring the time. Some people like to square everything like crazy. Don't do that. All right, and so that means y would be equal to, if I put this in my calculator, 0.5 times 9.8 times 2.3 squared That's going to get me 25.9 meters. So the answer to part A is 25.9 meters. So you see we had to kind of take the long way home to get there, but we did persevere. We did get there okay. How long does the ball remain in the air? Hint, the time it takes the ball to rise equals the time it takes to fall. So we used our free fall equation, V equals GT, to solve for time, and we know that it takes 2.3 seconds to go up. Well, how long does it take to go down then? 2.3 seconds. And if we add those two together, we get 4.6 seconds for our final answer. The symmetry of going up and coming back down allows us to figure that out, even just with the free fall time equation. Let's go to a coin flip. Excuse me. You decide to flip a coin to determine whether to do your physics or your English homework first. Obviously, your physics homework. The coin is flipped straight up. What are the velocity and acceleration of the coin at the top of the trajectory? This is a tricky one. We know that if you flick a coin into the air, as it gets to the top, it's going to stop momentarily. Stop momentarily. What does that mean? That means that the velocity at the top is 0 meters per second. I'll put velocity at the top. Here's the thing though, ladies and gentlemen. As the coin flies through the air, the entire time the force of gravity is acting on that coin, right? So that means the whole time the coin is accelerating. A lot of people would say, Mr. Simkins, at the top, the coin stops, and so the velocity is 0, and so the acceleration is 0. But guys, think about what that would mean. If you have no velocity and no acceleration, you don't go anywhere. What does that mean? That means if I toss the coin, and you were right about that, then the coin would go up into the air, and it would just stop and hover there. Now, that's weird, and when we say it out loud, it sounds ridiculous, right? Now, the acceleration is always down, all right? So let's consider this. On the way up, the velocity is positive, but the acceleration is negative. That's why it slows down. The velocity and acceleration are in opposite directions. Right at the very tippy top, here we are. Velocity is 0, and the acceleration is still 9.8 meters per second squared down. It's just that we happen to temporarily be at rest. And then that acceleration is going to cause us to change our velocity in the negative direction. We're going to gain negative velocity. And in class and in the lab, we talked about how the velocity versus time graph for this would look like this. You have a big upward velocity, so a big positive velocity. Up here, your velocity is 0, so at some point it would do that. And down here, you'd have a big negative velocity. And so your velocity time graph would be a straight line whose slope would be, you guessed it, 9.8 meters per second squared. Why? Because the acceleration is change in velocity over time, slope is rise over run. The slope of that velocity time graph for any object flying through the air would be 9.8 meters per second squared. So the acceleration is, it does say what is the acceleration, so we'll include the negative 9.8 meters per second squared. Let's look at the numbers in the equations here. If the coin reaches a high point of 0.25 meters above where you released it, what was its initial speed? It's a little tricky here. Okay, so what do we know? We know that y equals 0.25 meters, which we can use to get time. And you may say, well, why are you getting time, Mr. Simkins? Well, we know that v equals gt, so I can use that to get the velocity at the bottom, but I don't know time yet. So let's use square root of 2y over g to get time. Let's do square root of 2 times 0.25 meters over 9.8 meters per second squared. Let's take a look at that one. We got square root of 2 times 0.25 over 9.8. That's looking like 0.226 seconds. But the question didn't ask me for time, it asked me for velocity, so v equals gt. So that's going to be 9.8 meters per second squared times 0.226 seconds. Let's try that one out. 9.8 times 0.226. And the velocity there is going to be 2.21 meters per second. So that's how fast you have to throw it in order for it to go up a distance of 0.25 meters. Last part, if you catch it at the same height as you release it, how much time did it spend in the air? Well, check it out. We already knew that the time it takes to go up is 0.226 seconds. So the time it takes to come back down would be, you guessed it, double that. So, sorry, that looks terrible. Let me try that again. 0.226 seconds. You would double that because the time it takes to go up plus the time it takes to come down would be like doubling it. And that would be our final time for how long that whole kit and caboodle takes. So 0.226 times 2, that would be 0.452 seconds for time. All right? So, taking these ideas, you can still use the free fall equations. Sometimes you have to double time because time goes up, time comes down. Everything else is pretty similar though. So here's what I want you guys to do. I have this little problem for you. A kid jumps on a trampoline. If their super jump sends them 3 meters into the air, A, how fast were they moving when they left the trampoline surface? And B, how long are they in the air for? I want you guys to snip this problem and then upload it to the Canvas assignment that says Trampoline Kid Problem, and that will be your duty for this lesson. So until next time, this is Mr. Simkins in the Simkins Physics Corner.